So in order to ultimately simplify our definition of label tree awks and discover some monad structure hidden in here as well, as I just said, we first have to go to some intermediate steps that actually make things a little bit uglier. And the first thing that I want to do is I want to actually define a counter type. And actually perhaps we should again start by making a copy of label tree awks. So similarly, as we done all this way up here with 3 lookups, where we had the original version and we see where we ended up with. It makes perhaps sense to record this for posterity and keep a original version of label tree awks around. Okay. And perhaps also of label tree itself. Let me move that down here, and this one becomes label tree orig that calls label tree awks orig. Okay, so we are going to operate on these ones. And so what I'm going to do is I'm going to implement a new type synonym. This is perhaps, or not a type synonym, a new type. And I'm going to use a new type construct here because it's actually just a wrapped type. So it's a data type that has a single constructor and there is a single argument to that constructor. And the thing that we want to wrap up is actually this part here, a function that gets an incoming value of a particular type, in our case an integer, and then has an outgoing value of a particular type. So how do we do this? We have a constructor that I'm going to call makeCounter, and this constructor contains a function from an integer, and then it produces a pair of an a and an integer. So this is a bit unusual for various different reasons, right? So first of all, it's already strange to have a function type in here as a component of a new data type that we're defining. So let's actually just look at the type of the constructor once more. So if we look at the constructor makeCounter, it takes, as usual, it takes its argument. So that is in this case a function of type int to a pair of an a and an int, and it wraps it up in this counter type that we have. And we also need the dual. We need a way to extract the function again from a counter. We can define this using pattern matching. So we could define a run counter function that takes a counter a back into a function from into a int. And we can do this by just pattern matching. And then we have the function wrapped up in this constructor, and we just extract the function. But we can also use record notation for this by just saying this is like a one element record, and we call the field of that record run counter, and then the type of make counter is unchanged. It is still as before, and the type of run counter is exactly the other way around. It starts from a counter a and it extracts the function. Remember, the function arrow is right associative, so whether these parentheses around this part are there or not does not make any difference. Right? And now we can first do some sort of matching up on the type level. Right? So conceptually, label tree awks can now be seen as not being of type bin tree a to int to something, but first of all we can put these extra parentheses there for emphasis. Right? So it takes a bin tree a to a function that has exactly this shape. And now if we identify this shape here, then the first component of the pair is the result type that we're interested in. That is in this case the result type of the the counter-based computation. So that is a bin tree of a pair of a int. So we should be able to view this as a counter maintaining computation that results in a bin tree of a int. Right? And now, I mean, if you just see that a counter essentially stands for a function, like a counter a essentially stands for a function of type int to a comma int, then a counter bin tree a int stands essentially for a function of type int to a pair of bin tree a int comma int, right? So if we just expand it, it's essentially the same. It's all not type correct at the moment because obviously these types are sort of isomorphic, as it's called, but we need to explicitly convert between them, right? We need the make counter function to actually go from such a function to a value of type counter a. We need the run counter function to go back from a counter a to such a function. We are not applying these functions anywhere here. We're never producing anything of this counter type, so the whole definition at the moment is incorrect. Okay. But interestingly, perhaps somewhat, we now see that the relationship between label tree and label tree aux is exactly that they take the same input type, a bin tree a, and this one is creating a result of type bin tree a int, whereas this is like creating a result of type counter of bin tree a int. So this counter thing is exactly capturing this extra part that we introduced when we moved from label tree to label tree aux. This a fact that we have, in addition to the a, we have an extra integer input and we have an extra integer output. That is exactly what is being captured by counter. And actually, perhaps as a first step, we should actually try to make label tree type correct again. If label tree aux is now producing something of type counter, then it actually, we have to call it differently. We have to look at the types involved here. If we apply label tree aux now to the tree, right, then at this point we have something of the counter type, of the counter result type. That is the result type of the call of label tree aux. Now, if we want to apply this to an actual initial integer, we have to get the function out that we can apply the integer to. So we have to call run counter on the counter that we get out here. And now the result of the run counter call expects this integer. And we can feed the one that we directly applied up here to the call of run counter. And now at this point, the result of this whole call to run counter is a pair of actually, in this particular case, this here gives the exact instance that we're using. It is a pair of a bin tree a int and an int, and from that pair we still want to extract the first component in the end. So we could, if we compare the two versions, right, we just had to insert an additional call to run counter at the right position in order to make things type correct again. It is slightly harder to do the same thing for label tree aux because we have to move quite a few things around. So the first thing that is wrong, very objectively here, is that before we had been writing this as a function that takes two arguments. Right? On the left-hand side of the equals, we have two arguments in both these cases, the bin tree argument and the int argument. But now, label tree aux is a function that takes one argument and then produces something of type counter. So it cannot take two arguments on the left-hand side. So as an intermediate step that won't make anything directly better, let's just move over the incoming counter to the right-hand side as a lambda term. Right. It still moves it a bit closer to where we want to be because, at least in the empty case, we can now fix things rather quickly from here, because now the right-hand side of the empty case, if you look at this, is a function of type int to bin tree of something and a new int. And if we have such a function, we can just apply make counter to it and wrap it up as a counter type value as we want. Oh, make counter, not counter. I called the constructor make counter. And now you see the red lines underneath the line 124 right-hand side disappeared, so that part is actually fine. Okay. And we can try to apply a similar thing here as well. We can apply make counter and then do this and then let this function span the entire rest, and that makes things quite a bit better on the right-hand side as well. All right, now, not everything is underlined anymore, but only two places, namely the places where we have the recursive calls. And that is a similar situation as the one that we have already seen in the case of the wrapper function label tree here, where we now cannot just feed the counter directly as a second argument to label tree aux, because again, label tree aux now is a function that takes one argument, namely the tree, and then gives us back something of type counter, but that counter can be run in order to turn it again into a function, which then expects the integer input. So just like we inserted a call to run counter at the right place here, we have to insert a call to run counter at the right place here as well. So we get this and this. Okay. Now, things become a little bit more regular. And so we have a certain amount of similarity now, namely that we have these two calls to run counter here that looks a little bit like a repeating pattern. But in between, we have something that is a bit strange. We have this C2 equals C1 plus 1, or before we had introduced the C2, we even had that we had C1 plus 1 on the right-hand side here. And that is a little bit irregular as well. So that is kind of the next step to somehow press this intermediate operation, this reserving of a number for attaching to our current element, to press this into a particular shape that looks similar to the other things that we're doing as well. And we're going to do this by defining a function stepCounter, and the type of stepCounter is going to be counterInt. And the idea is that stepCounter is a counter-maintaining computation that results in an int, and the int that it gives us is exactly the value of the current counter, right? The current value of the counter, but it additionally also increases the counter by 1, so that the next time we would call stepCounter, we would get the next value. So how do we express this? Well, we have to apply make counter because we have to produce something of type counter. And then we get the initial, like the incoming value of the counter. Let's just call that C here. And then as the result of this particular function, as the main result, as the int result, that's the first component of the pair, we're going to use the current value of the counter, that is C. And then as the outgoing value of the counter, we're going to increment the counter by 1. So we're using the current value of the counter, but we are also incrementing it by 1. Now that we have been defining stepCounter, we can do the following change in our label tree aux function. Namely, we can do a call to stepCounter here, with C1, and what we get out is, let's say, the label for x, right? So let's call it label, or just perhaps LX, and a new incremented counter in this case. And then we use LX here. LX is going to be the same as, oh, and this is also wrong, dangerous, is going to be the same as C1. All right, so for the time being, this is another complication, but we are going to see more structure. That is exactly the kind of structure that we want now, that we actually align things even to make the structure even clearer. So we see that we have this let, and in every step we are having a call of run counter, and we now have an even more regular flow of the counter. So C0 is coming from here, it's going into the first run counter call, the output C1 is going here, it's going into the next run counter call, the output is going here, it's going into the next run counter call, and the output is here, and it's ultimately the output of the overall computation. And in every step we have a call to run counter with some counter maintaining computation, and in every step we get a result that belongs to that particular computation as well. The new labeled subtree here, the actual label that we are reserving for our element x, and the new right subtree here. And now there are no occurrences of the counter anymore that are not mechanically threaded, right? It's just coming in, it's passed to the first run counter call, it's coming out of it, it's coming out, going in here again, it's coming out of that, it's going in here again, it's coming out of that, and it's used here. So the counter use is now purely mechanical, and that means that we can more easily abstract from it. Let's at this stage perhaps reload and convince ourselves that actually things still work at this stage, right? Despite all our refactorings, if I now call label tree on my example tree, it still has the correct result. Right? It's arguably uglier than what we started out with, but it is a bit more regular, and that makes it easier to abstract from the recurring pattern. And that is the next step. We have now done all the necessary preparations that we essentially can proceed to identify the recurring pattern now. It is still not quite as easy as in the maybe case, but it is doable from here. And then once we have done that, we can proceed to drastically simplifying the definition again.